I'm making this video to give you a basic understanding of linear algebra so that you can apply it to a course in physics to find, say for example here, we're going to find a position vector in a Coulomb's law problem. Okay? So let us start by considering the following problem. Determine the electric field at point B, P, due to the wire of charge density lambda. So you can see the wire I have written down here, and I split it into two parts, A and B, and it's a continuous charge distribution. So I'm going to cut little chunks TQ and integrate along the wire to find the field. The field is given by this expression from Coulomb's law here, where this R vector points from the source to the field. Okay? And so we'll define two more vectors here, this R vector and this R prime vector, and we have this script R vector. And so the R vector points to the field, the prime vector points to the source, and if you subtract the prime from the unprimed, you will get this R vector that points from source to field. And you'll note in an introductory class, usually you just, for this vector here, this script R, you usually just use the R vector because you let the R prime vector be the zero vector, which means you're placing the point charge at the origin, which is easy, and they do that for simplicity. But here we can't do that. We need to use this script R vector because you notice that our charge distribution here is not at the origin. It's along these wires. Okay. So we can start off by finding the position vector for part B of the wire, this part here that is along the x-axis. So you can see I wrote it down here. I'm not gonna go through all of it to save some time. But the thing you'll note is that the final answer we get is a linear combination of basis vectors. And we'll talk about what that all means. Okay? And the other thing to note is that the x component you can see here of this field vector is actually of magnitude x. And why is that? Well, we're going to want to integrate it, this vector here, this field vector, we're going to want to integrate it from x equals 2 to 4. So this is why this is of magnitude x. Okay? Now we can also write this down in matrix notation, which we'll use later. That's good to know. So these column matrices here, these are called column vectors. Okay, vectors are matrices that have one column, okay, and the rows correspond to components. So here we have the R vector minus the R prime vector, and we subtract by row, and we get this final column vector here that describes our script R. And we can also write it down in vector notation here, which is the components separated by commas within these angle brackets. Okay. So the vector script R is actually a vectored value function. So you can see I defined it here. It's a function of x, and I wrote it down here. Same result. I'm just explicitly saying this is a function of x. We can put in x values and get these R vectors along the wire here. Okay. So this function takes a scalar as input and it returns a vector. Where the electric field is a vectored value function to say that takes in a vector as input and returns a vector. So this one has an input of a scalar, still gives you a vector, and where the electric field has an input of a vector and gives you a vector. There's vector value functions can be of either type. Okay. Now why is this a function of R and not script R? Well, we want the field at this point P, and I'm the observer at the origin, and I see the point P along this R vector. That's where I'm defining the point P at. Okay. It's all, this formula is relative to the observer. I'm the observer measuring the field at this point P. Now the equation for the electric field tells us that the electric field points in the script R direction, and is scaled by the amount given here. So I wrote this down as E is equal to A, which is a scalar multiple. That's A is this quantity here, times this script R. So what that means is the electric field points in the R direction and is scaled by this value here. So the electric field in this case actually points in this direction. Okay, and its magnitude, the value it's scaled by here, is based on that R vector and the scalar multiple. Okay. Moving on. The vector r that we calculated is commonly written as a linear combination of basis vector. Now let's talk about these terms. What's a linear combination? Well, it's a vector that is equal to another combination of vectors. It's a resultant of two or more vectors. And it's linear because its components are constant values. It's linear. Okay? So you can see the example I have written down here that we got from calculating along part B, where these x components and these y components are scalar multiples of the basis vectors. So the x basis vector is multiplied by the scalar quantity here. It's a scalar multiple. And you can see if I can actually write them as a linear combination, which is the plus sign. So I have two vectors here. This is r and negative r prime. And so this vector is actually a resultant. It's a linear combination of these two vectors. Okay. So I have another example down here. You can see this vector 2x hat plus y hat is a linear combination of the basis vectors x and y hat, where the x hat vector is a scalar multiple, so it's 2 times x hat. So if I go over 2x hat up 1 y hat, I get this resultant vector here. That's called the head to tail method. Okay. Now basis vectors define a coordinate system if their linear combination spans the whole space. What does that mean? Well, if I let these scalar multiples of x and y hat over here, if I let the scalar multiples be all real numbers, the resultant vector should hit every point in the Cartesian plane. These two basis vectors should span the entire coordinate system. So every coordinate system has a set of basis vectors that define that coordinate system. Okay? So let's move on and let's solve our problem. Let's find the vector r for part A. Okay? So here's how we do that. That r vector will end up being a vectored value function of x. And so you can see part A is written here. And the equation for that line is y equals 2 minus x. And if this were any other curve, you can write down the parametric equation for the line and get the components that way. So you just need the equation for this segment that you're going to integrate along that you want to find this vector for. So here's the r prime vector, and you can see its components as the x component of x, because that varies along this line. And the y component also varies, and so the y component is y, but we know the y is a function of x. So if I sub these two values here into the components, we should get x comma 2 minus x. And this tells us the r prime vector is a function of one variable, of x, because we can write down y in terms of x by looking at the equation for this line. So here I just write down the expression for the r prime vector, or for the script r vector, by having it to be r prime minus, or r minus r prime, and we get this final vector here. You go plug in values and try out and see it works. For example, 1, 1, the vector should point there. That is one of these position vectors along this wire. And so if I plug in, not here, I meant I would test it here. If I plug in 1, 1, you get 1, 1. Okay. You could test this too on your own. This is the easiest way of finding this vector. It's relatively quick. You just need to find the equation for this line so you can express this all in terms of one variable to integrate in one direction. Okay? So we only want to do a single integral for this problem. Another way that might be easier for some problems, not necessarily this one, is to find the r prime vector. The cumbersome is to consider the coordinate transformation. Okay, find an easier coordinate system to find that vector in. So here we go. I have my two basis vectors that define this coordinate system. This dotted line here is the wire, and it's easier to find the r prime vector in this coordinate system where I rotate it by a negative 45 degrees. Why is that the case? Well, you'll notice that if I draw my r vector anywhere along the wire here, the y component, this y prime component, is a constant. Turns out to be the square root of 2. We'll derive that down here. But it's a constant. And that's what makes this problem much easier to do. It's because, like when we did this first problem, we could tell that this y value here was a constant. It was 0, right? And we just had to throw in x as the scale along this x direction. Okay? And so it's the exact same thing here, right? Our x changes, but our y doesn't. And this just makes this problem more simpler to do it with this rotated coordinate system. So step 1 is to find the change of basis matrix. Okay? Where what this matrix actually is this first column here is your new basis vectors written down in your coordinate system. and this is the x basis vector, the x prime basis vector written down in our coordinate system, and this is the y prime basis vector written down in our coordinate system. So it means if I were to take these vectors and find the x component in our coordinate system and the y component in our coordinate system, this would be the components. Okay, so what I did down here with this drawing is I took this y vector and I drew it over here, and then I scaled that up. And so all I do here is I just do some trigonometry, you can see, and I find that I just wrote down a general expression. This in terms of x's, even though this picture is in y's. But what I said, for example, is that x prime is cosine of 45 degrees times x. So x prime would actually be right here, and you can see that it's the same for this y prime. Actually, y prime is also equal to the cosine of 45 times y. And so what I do with these expressions is cosine of 45 is 1 over the square root of 2. And so I find this for all these vectors, and I put them into this change of basis matrix. Okay? So all I'm doing, again, is I'm just expressing these components in terms of our coordinate system for this change of basics matrix. Here's the x prime component and the y prime components. Okay? And you just do some trig to find it. And the other thing I want to point out is people commonly just draw this to this lattice point here, which is the position x hat plus y hat, and it's actually not. This is the same unit vector. It's a unit vector. I just rotated it. It's of length 1. So know that. So this length here, this distance here, is actually the square root of 2. Okay? So now let's find our prime in our primed system. Well, how do we do that? Well, let's look down here. We can identify that, like I said, this y direction here, is actually the square root of 2, which is a constant. And then we just have the x varying. So there are the components. The x component is x prime, and the y component is the square root of 2. So now that we have the vector written down in our new primed coordinate system, and I want you to note that this r prime is not the same r prime I was talking about before from up here. This is the source. Okay, I'm just calling this the unprimed and the primed coordinate system. Okay, I just didn't want there to be confusion. So now we want to transform this r prime back to r, to the unprimed coordinate system. So here's how we do it. We'll use this linear algebra expression here, which says that this vector in the unprimed coordinate system is equal to this change of basics matrix, which will operate or multiply on this primed vector here. And so the way we get this expression here is matrix multiplication works by to find this first row, we take the dot product of this vector in the first row. And to find the second row, we take the dot product of this vector in the second row. And we get this expression, which I can then say that x is equal to this first row and y is equal to the second row. And here, this is the coordinate transformation between unprimed and primed. That is how you derive a coordinate transformation. All of this we just did right here was deriving this coordinate transformation. Now that we have it, we just plug in our vector components, do some algebra, and you get the exact same vector that we got up here. Okay? This one right here. x2 minus x. x2 minus x. All right, so those are the two ways of finding your source vector using some linear algebra.